Hello everybody, this is Miss Smith. Today we're going to be talking about skill 9.6, which is going to be over magnetism. As always, please make sure you have something to write with and your notes in front of you, whether that's a blank sheet of paper or the notes from the haiku site, or again, you can type them as usual. Please take a moment to celebrate that this is the last skill for ICP. So we have today, which is the 9.6 notes and IP that you'll be doing, as well as the quiz that is going to be next time. And then next time you're also going to have a review activity over this final unit, which is unit 9. And then we're done. So let's go ahead and get through this last skill. As always, if you have any questions, please let your teacher know, come into, pop into our office hours or email us or whatever works for you. So let's go ahead and get going. So today we're talking about magnets. So these are objects that put a magnetic force on other objects. Luckily, you know what magnets are already, right? So you can visualize kind of what's happening here. So you know that sometimes you can have a magnet and it will stick to some things and it doesn't stick to other things. Okay, so today we're going to talk about why that happens. So objects that are attracted to the magnetic forces are magnetic objects, right? So you can take your magnet and stick it on your fridge because your fridge is a, metallic object, or magnetic object. So some examples: other magnets, metals, or something that has moving charges or current with it, right? So those will be attracted to a magnetic force, right? So they are magnetic objects. Objects that are not attracted to the magnetic force are called non-magnetic objects. So if you have that same magnet that you had earlier and try to put it against your wall, it probably won't, get stuck to it, right? So wood, plastic, cloth, something like that, magnets will not stick to those objects. So they are called non-magnetic objects. The magnetic force is the strongest at the two poles of a magnet. So you have a north pole and you have a south pole, right? So let's say we had a bar magnet here. Yay. You have a north end and you have a south end. This is where the magnetic force is the strongest. There's still magnetic force all over this magnet, but it's the strongest at the two poles, north pole and south pole. Every magnet will have a north pole and a south pole. So as we know, opposites attract, so opposite poles will be attracted to each other. So let's say we had another magnet right here. We have south here, so if we want these to be attracted to each other, we have to put north here and south here. Now this object will be attracted, right? So they'll kind of pull towards one another, right? They'll want to stick together, okay? But if you were to take this second magnet and flip it around, instead making it look like this, so we have our south pole here now, and now we have our north pole over there. Well, south and south are lining up together and they don't want to be near each other. They're going to repel away from one another, okay? So instead of being pulled towards each other, they're both just going to push away from each other. That's why sometimes when you have two magnets, you're trying to push them together, but even though they're not touching, you can feel them pushing away from each other, right? They don't want to go close together. It's because you have the two south ends or the two north ends lining up together, right? So if you break a magnet in half, it creates two new magnets, both that have a north pole and a south pole, okay? So this is one really interesting property about magnets. So let's say we start out with this one. We're gonna have north here and south here. Please make sure you're writing this part down because you will see this again, all right? North there, south there. So let's say we take this magnet and we break it in half, okay, right down the middle, as we kind of see in the middle here. So now we still have north here. It didn't go anywhere. South is still going to be over here, okay? Those didn't vanish, right? But now that you've broken it in half, now you have another south end here because this magnet needs a north pole and a south pole. And this second magnet also needs a north pole and a south pole. So now you have two new magnets. Both of them will have north poles and south poles, okay? Let's say we break it in half again. Take these two magnets, break them both in half. So north is still here, south is still here, all right? This south is still here, this north is still here, okay? They didn't go away. Now you have four smaller magnets. So each small magnet must have a north and a south. So north and south, north and south, north and south, and north and south, okay? Four new magnets, they each will have a north pole and a south pole. So this is possible because magnets are made up of tiny, tiny magnets, and these are going to be called magnetic domains, okay? So, right, we have two kinds of object. If an object is non-magnetized, so non-magnetized objects, that means then these domains are all pointing in different directions, right? So there's no overall north and south. The way that we're going to see these is we're going to have a box like this broken up into different sections with arrows in them. So in a non-magnetized object, let's say one's going this way, one's going this way. You'll always see these as arrows. One's going this way, this way, this way, this way, and that way, okay? They're all pointing in different directions, so overall, there's no big push in either direction, right? They will cancel out with each other, so there's no overall north and south pole. This is why you have a non-magnetized object, because in these magnetic domains, they're all pointing in different directions, okay? However, in a magnetized object, all the domains are pointing in the same direction, so there is an overall north and south, okay? So what you'll see here is you could see something like this. They're all going to be pointing in the same direction, okay? If they're all pointing in the same direction, that is a magnetized object. In this scenario, all of the arrows were pointing to the left that way. I could have easily drawn them all pointing to the right or all pointing up or all pointing down, okay? The direction of the arrow doesn't really matter as long as they're all pointing in the same direction, okay? So this still would have been correct if I would have drawn it, you know, with all the arrows this way, for example, okay? As long as they're all pointing in the same direction, it is a magnetized object with an overall north and south pole. Now, the magnetic force put off by the magnet follows the magnetic field, okay? So the magnetic field, that's why when you put two magnets, like two south ends together, you can feel them pushing away from each other. It's because they have this, to our eyes, invisible magnetic field around them, okay? So the magnetic field, the force and the strength of the magnetic force, okay? So we're going to draw these using magnetic field lines. We're going to draw several examples of these in just a moment. Basically, they are just lines pointing in the direction of the field, all right? And they follow a very specific pattern. Magnetic field lines flow out of north and into south, okay? So they will always go from north to south. It will always point from north to south, okay? That is the critical piece there, from north to south. So let's say we have this situation. We have our bar magnet in the middle, we have our north end and our south end here, okay? As you can see, all of these lines, these are magnetic field lines here. These are all magnetic field lines. And they are all pointing from north to south, okay? So they're going out of north and into south, okay? So if you can follow all of these, and they will all go from north to south. Even the ones over here, they're just going above where the picture is, and then they're gonna come back around and then land right here, okay? They're gonna wrap around, always go from north to south. That's the big piece here, okay? You don't really have to draw all of these extra ones coming in here. You can if you want to, but you don't necessarily have to. Now keep in mind, as we are going through this, we can't ask you to draw these. So really the critical piece here is you need to be able to look at this picture and say, okay, is it accurate or is there something wrong with it? Okay, that's what you need to be able to recognize. The key thing, you have to have a north end and a south end, and the lines need to go from north to south, okay? Then you'll be good to go. So let's practice this. So we have our magnet here in the center, our north end here, and our south end here. We need to think about, okay, if we're going to draw these magnetic field lines, what will they look like? Well, we just said they will always go from north to south, okay? There's not really a specific number of these lines that you need to draw, but they're going from north to south. They're going to go out of north, all the way over, and into south, okay? So we're going to draw a bunch of these. Now, keep in mind, you could also draw them with these little arrows kind of halfway. You don't necessarily have to, but it might be a good practice. So from north to south, all going in this direction, okay? So you can add, again, you can add as many of these as you want to. They're going to get messier the longer you go, just because you're going to need more room, right? But you can draw a lot of these. From north to south, magnetic field lines. So you can see this happening in real life. So if we were together, we could have done this in class, but unfortunately with our circumstances, I get to show you a lovely picture. So iron filings act as mini magnets and can show you magnetic field lines. So you have these two, ends, these two poles right here. And you can see them kind of creating those lines that we were drawing earlier, right? So all of these magnetic field lines that we were drawing are still coming into play. Okay, a magnet can also be created using a moving current, a wire, a metal object, and a battery. So kind of going back to when we were first doing circuit diagrams and circuits and things like that, we have our battery here, and then this is our wire here going through this nail, which is acting as our metal object. So if you coil a wire around a metal object and give it current from the battery, right, battery will give that current, the wire is going to create a magnetic field. So again, if we were in class together, we could show some cool stuff that would pop up here, but really you just need to know that you need these different objects and you can create a magnet. All right, so do now. If you have not already done so, go ahead and do the 9.4 and 9.5 quiz over series and parallel circuits. If you have not done so already, make sure you get that taken care of. And then the 9.6 IP, which is over magnetism, which is the skill that we did today. Keep in mind, if you do have any missing work that you have not turned in yet, please turn it in as soon as possible, just so we can get it graded and updated into your PowerSchool as soon as we possibly can. We are almost done. Please stick with everything. And again, contact your teacher if you need any help.